Ladies and gentlemen, my talk today is about human agency in quantum age. First and foremost, I'm going to tell you a little bit about this absolutely wonderful domain of quantum computing and quantum information. But my real goal is to prove that we still matter, that we matter even more in the quantum age. To understand that better, let's review what really this quantum age is. The first quantum revolution started 100 years ago, in the beginning of 20th century. We reviewed matter at atomic scale. We learned about wave-particle duality, tunneling, wave functions, and many strange phenomena that gave rise to semiconductors, lasers, computers, internet, mobile devices, and finally AI. And they form the information age we all live today. Now, around 2000, we realized that we started to live in something we could call second quantum revolution. And the second quantum revolution is where we can control the microscopic world. We basically can use quantum mechanics to change the quantum phase of the world. Paradoxically, it all started from big controversy and shock. None other but Albert Einstein, who, by the way, was father of quantum mechanics, got Nobel Prize for co-invention of quantum mechanics, wrote an article in 1935, Can quantum mechanical description of reality be considered complete? And as you can take from this title, he supposed it cannot. It was so shocking that even popular press wrote articles, Einstein attacks quantum theory. That was really a shock to the community that such a person could question the domain he helped to build. We waited about 30 years when Irish physicist John Stuart Bell proved amazing theorem where he proved that extremely simple inequality, classical inequality, can be tested experimentally. And if this inequality is violated, we can prove Einstein wrong or right. We waited another 10 years, 20 years, when such experiments were finally conducted. And what they showed? Violation of Bell's inequality, proving Einstein wrong. So what he was wrong about? He was wrong about something which we called local realism. He was wrong by denying the ability of quantum objects to signal things or to actually be correlated at the long distances, something we call entanglement. Finally, it led to a Nobel Prize in Physics in 2022 and the birth of amazing domain of quantum information. Quantum information sciences have three pillars. One of them is quantum computation, with quantum computers as a main object of that domain. Second is quantum sensing, with quantum metrology, or ability to measure tiny little signals, like quantum radar, for example, using quantum technologies. And the third one is quantum communication and quantum cryptography to protect our data. Let's start from going a little bit under the hood of this beautiful domain. So in classical space, in classical computers we have bits. Bits have two states, -5 volt, +5 volt, magnets up, magnets down, whatever physicality is used, it's always two states. Quantum bit, called qubit, on the surface has also two states. We call it 0 and 1, or vector 0, vector 1. But they are actually in superposition. And that, in practice, means that they can exist in infinitely many states at the same time. The beautiful description of what qubit is comes from Tim Spiller, professor from University of York. And he said that if you imagine that the classical bit is black and white, then quantum bit, qubit, can shine in every color you can imagine. I brought a little demonstration to show you this. Let me try. Oh, my beautiful stick doesn't work very much. Okay. But anyway, it still will work. So this is classical, 0 and 1, right? It's a mathematical abstraction of all computers we have is just 0 and 1. Quantum bits can be best represented by vectors in space. These vectors can rotate. So when we do operations on them, they rotate. We have a special sphere, which we called block sphere, where these vectors are represented because they are always units. So we can have like a sphere and perform all the operations by using that kind of representation. Now, if you go to what is the heart of every computer, are gates. We know that. I mean, there are logical gates in classical computers like AND, OR, NOT. Quantum computers also have gates, but these gates do totally different thing. What they do, they literally rotate these qubits. Well, qubits are not rotated. This is mathematical representation, don't forget that. But we can imagine that in such a way like we imagine that 0 and 1 form logical structures. So in quantum space, the representation of qubits is a rotation of these objects in mathematical space. Unusual capacity of quantum computers comes exactly from one of these points. So when classical computer with n bits is in one of these multiplicity of states, just one, then quantum computer with n qubits is in all of these states at the same time, all of them. There is caveat here, by the way. If we measure such a qubit, of course, it becomes bit. So that's only exists when we conduct computations, not when we end them by measurement. We call that quantum space expansion, and this is one of the reasons of this unusual capacity. The second reason is existence of special algorithms that are very fast. But here is a warning. Not everything, not all algorithms can be made faster by quantum computers. Do not expect that you have Excel sheet in the quantum world or that your laptop will be quantum in the next couple of years or even decades. Not at all. However, there are some specific algorithms that show absolutely incredible speed up. I took only two because they are the most important still. Search, which can be made faster by quadratic form, so square of the speed, and factorization. Factorization is breaking big numbers into divisors. This is very important for cryptography, as I will show you. And this algorithm can be exponentially faster. Actually is, because we know that they run on existing computers. You can become familiar with qubits and quantum gates and basically with quantum computation by multiplicity of different tools, simulations on the web. Almost all of them are free. Quark is perhaps the best, where you can draw qubits, draw gates, and really feel how that whole machinery works. You can also play with a bit of fun with that. There is a first open source quantum board game. You download PDF, you print it, and you can play with your friends, learning this incredible domain with a fun. Of course, quantum computers today are real things. What you see on this slide are commercially available quantum computers for multiple different vendors. Some of these vendors achieved recently huge boost on NASDAQ, for example. So this is extremely important domain. By the way, two of these computers are already in Poland. So this is very, very important also for us. The breakthrough that we see this year, so this is a very special year for quantum, is that key players in the domain brought quantum chips. Quantum chips are like building blocks of future quantum computers, bigger computers. They come from Google, from Amazon, from Microsoft, and even from University of Science and Technology in China. But what is extremely important about these chips is not necessarily the number of qubits or the size of a speed, is accuracy, is error correction, is fidelity and long coherence time. Basically, the goals of these chips, like for example, Microsoft has only 8 qubits, but probably this is the most important chip ever invented in quantum space because of this long operational fidelity. That may actually break the spell we have on computation today in quantum, because all existing quantum computers, we call them NISQ, noisy intermediate scale. What that means? Qubits are prone to errors, so they are noisy. We have a lot of errors. We have limited scale computation. Error correction is poor. These chips and other inventions may bring, and actually are bringing today as we speak, something we called FTQC, fault-tolerant quantum computing, where fault tolerance and long computation are norm. They allow for universal quantum computing. What are the applications of these devices? First and foremost, as any big technology in humanity, there is dark side. Atomic energy brought atomic bombs. We know that. So is with quantum computers. Unfortunately, these algorithms that I am still going to tell you a little bit more about, Shor and Groover, they are posed to break cryptography. The Cloud Security Alliance, which is far from hype, the organization that protects clouds, predicts that that may happen in 4 years. More realistic predictions that I buy is from 4 to 15 years. However, when this moment comes, it will be too late to respond. We need to do something now, even also because our enemies have strategy, which is called SNDL, Steal Now, Decrypt Later. I don't want to name countries who are doing that. You probably know that, but it's really in place. We must act now. That means we must adopt quantum-resistant cryptography, which we can do today. And fortunately, both United States and European Union, this is extremely strong process right now. And I'm very happy that my little startup that I launched in the end of my scientific or entrepreneurial career is exactly in this space. There are better side of quantum, of course. The quantum algorithms, quantum computing is extremely important for pharmaceutical industry because it can help new drug designs, materials engineering, automotive automation and robotics for optimization and management of these resources, aerospace industry, defense and security, and even banks, financial services can benefit from better and faster algorithms. And last but not least, I call that always killer application for quantum, AI. Why? Because we know how to use AI. We do not need to invent anything. If we can make AI faster by applying quantum, we are much better off. I also brought now a very important part, case studies, these 2 algorithms that I say are so important. But not to impress you with details of math or quantum science, my goal here is to show you that to invent this algorithm, we need out-of-box thinking. We need imagination that create breakthrough and not algorithmic approach. So Peter Shor, working for IBM in 1994, brought the algorithm for prime numbers factorization. That means that these big numbers can be divided into primes or found if they have such a divisor. And Love Groover, just 2 years after, published the article where he proposed this algorithm for fast search. What is amazing here, this is before any quantum computer existed. So they were working completely theoretically, and these algorithms now run on realistic computers, so shows their genius. These algorithms are, as I say, dangerous. Shor breaks asymmetric cryptography, which we know from digital signatures, and Groover can weaken, not break, but weaken other forms of cryptography, so extremely dangerous. However, to invent them, we need something which is a central part of my message, paradigm shift. So see what Peter Shor did. He said, okay, let's take a number we want to factor. Let's turn this problem into problem of finding a period of very long sequence. This was known in science already, so that was not that genial. What was really a stroke of genius was the fact that when he said, okay, we have a period, so it's like a spectrum. So what we do to find the peak of a spectrum? Interferometry, like we measure the sunlight and the peaks on the spectrum of a sunlight. He said, let's use quantum computer as a kind of computational interferometry. Totally out of box, totally out of blue, and indeed that worked. And once we have a period, we can use classical computers to find the factor, and we have a factoring algorithm. Equally fantastic is the Groover from the ideation. He said, okay, let's make the value we are searching for prominent. Let's make it amplified, and let's discard other values that are perhaps not contributing to what we search for. And this has amazing analogy in thinking to the problem of finding the exit from the labyrinth or from maze. In the classical space, it's like you have Ladybug going across this labyrinth trying to find a way. Okay, she will find it, but after many, many paths. She will probably may even try all possible paths until she finds the exit. Now, Groover algorithm is like you put the ant colony at the same time on this labyrinth. So, okay, not all ants will exit, but some of them will do. And we have the exit. So that's this, again, paradigmatical shift here that happened in thinking about algorithms and applying analogies, applying mechanisms that are not known in the classical algorithm building. What characterizes this paradigm shift essentially? We go from deterministic thinking to probabilistic amplitudes. We break from classical Boolean logic into quantum linear algebra and quantum logic. We forget sequential thinking into parallelism. We go from debugging, which is a tool for programmers, to designing evolutions. And last but not least, we are reframing algorithm, which is today a recipe, into algorithm as quantum circuit, with completely different way of thinking about algorithms. There are some astonishing facts that make this domain even more stranger. We have no standard memory model. We cannot copy data in the standard way. We have a fantastic concept of uncomputation. What it is, if you imagine that computing is rotating this qubit, then uncomputing is rotating back. You can do that always, right? It's a reversible computation. So uncomputing is very interesting fact on that. Now, spooky action and the distance that Einstein was problematic with, entanglement and interference are our important resources in building these algorithms. And probabilistic results are core of what we get in the end, not numbers. And for those who are coders here, compilation is not code generation in quantum. It's a different thing. So the conclusion is, quantum programming brings the largest paradigm shift in software development since the invention of digital computer. The big question, what really paradigm shift is, in essence, it's when old thinking can no longer predict new solutions. This is why, that's my claim, we need us humans. Okay, but big question is, we have AI, we have ChatGPT, we have Copilot, we have multiplicity of tools for software development. Can AI spark paradigm shift? Can it invent something? And so far, thanks, I don't know to whom, the answer is no. And actually that was proven experimentally. Researchers built time-boxed language models. Imagine ChatGPT learned only on the knowledge up to the end of 19th century. And the question was, can such a model predict what happened after? Can it, for example, imagine quantum mechanics? And all the tests that were done so far show no, it is not possible. Will it be in the future? I want to have as an open question. I do not believe in that. So what makes us humans irreplaceable in the quantum era? We are irreplaceable in this quantum age because quantum programming requires human judgment and mental models. We need curiosity, courage, conscience in this time of paradigm shift. We must use analogies, metaphors, taste, and be responsible. And the machines don't have that things. So we are conscious beings. This is why we form mental models. Machines do not have. So the conclusion is that human agency is a decisive factor in making quantum technology useful, reliable, and aligned with our goals. Humans at the quantum age are at inflection point in this domain and in all science, in technology, that's obvious, but in this quantum domain, I just tried to prove that this is the case. And I will end my talk today with a call to human agency. Let's build the future always on purpose. Let's choose direction, but what that means in practice is define why we build before we say how to build. We must invest in young people, open tools. Why? Because this is where paradigm shift happens, where we think out of a box. We need to make quantum technology useful and safe, and that means that meaning must be anchored in human judgment, because technology multiplies our power, but only we can decide what counts as a progress. So let human agency be the compass at every paradigm shift, including that big one, quantum age change of models of thinking, models of programming. Thank you very much for your attention.